In this video, I'm just going to talk about a problem. We're going to find the mass of a deuterium using the energy principle, okay? So I have this problem here. So the proton, its mass is 1.7 times 10 to the negative 27. This should be 27 kilograms. And then neutron is also 1.7 times 10 to the negative 27 kilograms, and they're at rest. They both combine to form a deuteron, the nucleus of a deuterium, okay? And the process of gamma ray is emitted. Okay, its energy is measured to be 2.2 times 10 to the 6 eV. What is the mass of the deuteron? Well, if I'm looking at this problem, I'm going to use my energy principle. So I know that the change in energy of a system is equal to the Q plus work. Okay, we know there's no work external, and we know there's no heat being transferred. So therefore, delta E of the system is equal to 0. Okay, now if that is true, then we know that E initial is equal to E final. Okay, now what do we have initially? Initially, we just have the proton and neutron at rest. And so if we want to look at this, we know E initial has to be equal to the rest energies. So this is mc squared of the proton plus mc squared of the neutron. So that the only thing they have is their rest energy initially. Okay, what do we have E final? Well, look, because they both combine to form a deuteron or final, we have the rest energy of the deuteron. So this is mc squared of the deuteron. Okay, what do we also have? We also have the kinetic energy of the photon because a gamma ray is emitted. So we have the kinetic energy. Remember, photons have no rest energies, and so the rest energies, it's 0. There are no rest energies, and so we could omit that rest energy thing here. Okay. Now, what else do we have? We also have the kinetic energy of the deuteron itself. Okay. So those are all the stuff we have final. Okay. Now, the kinetic energy of the deuteron, it doesn't move that much because it's so big, and so we could ignore this. So we could say this is approximately 0. And so if I'm looking at this, we could set these equal to each other. And so I have mc squared of the proton plus mc squared of the neutron, and that is equal to mc squared of the deuteron plus kinetic energy of the photon. Now, what were we solving for? We're solving for what is the mass of the deuteron. So we're solving for m, for this m. So let's put an underline behind it. And so if I take mc squared of the proton plus mc squared of the neutron and a minus my kinetic energy of the photon, well, that's just equal to the mass. If I divide this by c squared, then this becomes c squared. So the mass of the deuteron is equal to all this divided by speed of light squared. Okay, and again, mc squared, what's the rest mass of the proton? What's the rest energy of the proton? 1 times 10 to the negative 27. Okay, and the speed of light 3 times 10 to the 8 squared. Okay, so we get 1.53 times 10 to the negative 10 plus 1.53 times 10 to the negative 10. And the rest energies of the proton and neutrons are actually the same. I'm going to minus that from the kinetic energy. Well, we know that kinetic energy is 2.2 times 10 to the 6 eV. Well, we're going to convert that to joules because rest energies are actually in joules. Okay, and so we know for every let's do it here. So we know for every 2.2 eV, well, for every 1 eV, we say we get 1.6 times 10 to the negative what? I think I have a conversion unit here. So for every 1 eV, we get 1.6 times 10 to the negative 19 joules. I forgot my 19 joules. Okay, and so if I multiply 2.2 times 10 to the 6 times 1.6 times 10 to the negative 19, I get 3.52 times 10 to the negative 13 joules for my kinetic energy. And I divide all of this by the speed of light squared, 3.0 times 10 to the 8 meters per second squared. And that's in joules. So if I take all of that, that will equal to the mass of the deuteron. And so if that is true, then if we take all this, subtract it, add, subtract, and then divide, then we get the mass of the deuteron to be 3.34359 times 10 to the negative 27 kilogram. So it's really small. Okay, so that's the idea. Now, there's just something I want to point out just aside here. With decay problems, and this is not really a decay problem, it's similar. Let's say we have a neutron here, and it decayed to give us a proton, plus, I don't know. So it gives us a proton plus electron and plus a neutrino. Okay, so let's say this is a neutrino. Okay, here's what I want you to remember. The neutron's rest energy is equal to the sum of the rest energies of the products plus the kinetic energy. That is something to be very careful of. Okay, the rest energies, the rest mass of the neutron, the products of these will actually, in order for me to get the rest mass of the neutron when it decays and scatters, I have to add their kinetic energies plus their rest energies. And so usually, when we do these types of problems, we say, okay, well, the rest energies doesn't change, so we could cross them out. But in fact, when we deal with decay processes, so decay processes, okay, decay processes, rest mass, rest energies actually do change. So be very careful. Don't assume that those are zero.